In this video, I'm going to cover the transmission mount that I fabricated and use of the Stomsky racing mounts, which have two urethane blocks in them on a machined aluminum housing that I'm mounting into the transmission mount that will bolt to the trailing arm, the bottom of the trailing arm mounts. On this side here, I show you one of the Stomsky racing engine mounts bolted in, loosely fastened into the 1/4-inch plate steel. So the order of business is the following. This is 4-inch wide, 1/4-inch plate steel. All this is all 4 inches here, this template that you work from. You then get, this is a 72 millimeter hole that was cut in this 1/4-inch plate using a 72 millimeter hole saw. In fact, here it is. It's made by Malum. It's actually a pretty good one that I ordered off Amazon. It's quite strong. Carbide tips in it. 72 millimeters. So you, in this 1/4-inch plate, you measure out, you want about a 1/2 inch delta here, 1/2 inch edge, and leave about an inch on one side here. So wider here and then about a 1/2 inch in the outer. This is naturally going to be close to a 1/2 inch. So you drill your 72-inch hole in your 1/4-inch plate, as shown here. You do that 2 times, once here on this side and once on this side. On this side, you can leave about a 1/2 inch on each edge of the hole. So about a half, 4 inches wide. Overall, probably 4 inches wide here. I wasn't really concerned with that. And then a little bit more meat on this side. When you're looking up on the car, this is going to be towards the front of the car, and then this is the passenger side, and it'll look like, actually like this when you're looking up on it. It'll look like this. So the front of the car will be here, pointing this way, and then this will be the passenger side, and then you're under the passenger side and then driver's side over here. So back to where we were going. You cut out your 72 millimeter holes in these 2 edge pieces here, and they're by themselves. So it's approximately about 4 inch by 4 inch, 4 inch by 4 inch. Make this longer, so probably 4.5 for the total lengthwise this way. Leave about an inch on this distance for this piece. Then you're not even concerned with this center piece yet. You then, with your Stomsky mount in this edge piece here, in this square piece here, you bolt this piece of plate steel that's only 4 inches by 4. It's not welded on yet. You bolt this with the Stomsky mount into the bottom of your trailing arm with this. This M12 bolt now goes right up into your trailing arm. Then you come up in the top of your trailing arm mount and you fasten the nut, tighten that down. You don't need to torque it because you're not completed with the job yet. Just firm it down, make it snug. Then you do that, repeat with this side. Put your Stomsky mount in. The top piece. The bottom urethane part. Then your washers on top. Washer on the bottom. Then your M12 bolt through this. Through the top. Spin it upside down. And then bolt your M12 through the bottom of the trailing arm mount. That's a M12 hole that you're going through. Then put your nut on and snug it down. You now have these two 4-inch 4x4 pieces of plate steel with 72 millimeter holes in them. You now have these bolted to the bottom of your trailing arm mounts. Okay, your transmission can be in when you do this. So you snug these up via the Stomsky mounts. Then you cut out a piece that's approximately, say from my setup, we're looking at about 8 inches long, 8 1/4 long, right? 8 1/4, 8 inches here, depending on what you're going to do. And then you go to the nose of your transaxle and look at those threaded studs, and then measure those out, and then drill those in this piece. So now you have 3 pieces of plate steel that are separate. The 2 edge pieces, and then the center piece. You bolt then you drill these. These are M10 holes, metric 10 millimeters. You drill these 4 holes. Then you bolt this. Then you have to cut this for the 930 nose of the transaxle. I had to cut this out. So because the transmission, the cast aluminum for the transmission is right here, occupying this space. So with this little divot cut out here, you then bolt this onto your transmission, this 8-inch piece here. Then these smaller pieces are not welded in yet, obviously. And then when you look up at you're looking up, what you're going to see from the bottom is this. This will be bolted in the bottom of the trailing arm mount. This is bolted into the bottom of the transmission. You then take a piece of cardboard and cut out a piece of cardboard that will fit between the edges of this piece and this piece here. Then you go to this side and use cardboard aided design, CAD or CAD again, and cut out a piece of cardboard that spans the distance from this edge of the 4x4 piece here and this 8x4 piece here. You're cutting out this cardboard piece right here. You then tack, once you've cut those out on your shop bench, you leave these remain bolted in the car. You measure these with cardboard templates, go over to your shop bench and cut those out. You then come back, you then grind up the edges of them, like here. I don't know if you can see the lighting here. When you're going to weld steel plate, you have to grind. You have to sand off or use a die grinder with an emery cloth on it and grind off about 1/4 inch off the edge on the sides to establish a good electric conductivity for the arc. So you clean that off all the way around wherever you're going to have welded beads. So clean this off on the bench. You grind down on the bottom as well. You clean this off, clean this off. On these pieces that you cut out here, you clean off the mill scale off the edges of that small piece, and then grind off the mill scale on the edges of this small piece, where this is called mill scale. It's coated on the steel at the mill to prevent corrosion and rust. So it's all over. You can see a little bit of surface rust coming through in this piece, but it's called mill scale. And wherever you're going to weld on steel plate, you have to grind this off so that you can see the fresh virgin steel in order to establish optimal electrical conductivity when the arc is struck, to establish a good arc. You don't ever want to weld plate steel or even steel that has mill scale on it or anything. You never want to weld steel without grinding the edge where the arc is going to be formed, because you want maximum conductivity to ensure strength and reliability and durability of the welds or the beads that you lay down. So then once you go to the car and you then hold they'd be hard to hold with any type of a clamp. So then with your welding glove on, well, this is bolted in the bottom of the trailing mount and this is bolted on the bottom of your transmission. You naturally have a lift under your engine and your transaxle. You then weld with a tack just in these 4 corners. So you tack weld right here, and then here, with this piece held, you take your welding glove, hold this piece, and then tack right here on this, tack right here, and then tack this, tack that, and then finally let go, and then tack this corner, and then tack that corner. Then you come to your shop bench and you use 7018 steel rods, which have a tensile strength of 70,000. And you first, as I've shown here, you can see there are 3 beads. You can see 3 beads run right here. You can see those 3 stringer beads. In this corner, you first run a root pass with your 7018. I had 1/8 inch rods. You run a root pass down in the corner, and then I laid down 3 stringers next to one another over that root pass. Once you lay down your root, now you have to use arc welding. The word is with plate steel that arc welding should be used. Anything that has to support very strong structures, like construction work, building a building or building a metal frame for something that has to hold a lot of stresses and is structural steel, you should use arc welding, not MIG welding. So 7018 steel rods are the go-to for welding plate steel all day long, 7018 rods. I ran a root pass with a 7018 1/8 rod and then 3 stringer beads over that root pass. Every time you run a pass, either the root or the stringer beads above the root pass, you use a wire brush to clean off. So you chip away with your flux hammer and then remove the flux, and then you run past that with a wire brush, a wire wheel, clean it off, and then over your root pass you run 1 stringer bead. And then clean that off, clean the flux off, wire brush it, then run your 2nd stringer bead, and then your 3rd stringer bead, and then finally you're done. And you can see that on any one of these corners I ran 3 stringer beads. Not just 1 bead, but 3. And down in that corner, there's 3. There's a root pass and two top passes because there's not a lot of room on that one. And then here are your three stringer beads here. So a root pass. This is a root pass and 2 stringer beads on top. So there you have it. That is how I fabricated out of 1/4 inch low carbon steel plate my transmission mount for a 68 912 with a Porsche 930 Transaxle mounted to the LS engine, with the LS engine bolted in the rear engine mounts, and everything set up as if I was going to finalize the setting of where the transmission mount is. Oh, and by the way, this Allen bolt here, this M12, is a 12.9 class, which has something like 100,000 pounds of tensile strength. So it's very, very strong. These M10 bolts, or these M8s here on the edge of the Stomsky mounts, are M10.9s. So they're about 70,000 pounds of tensile strength. So they're quite, structurally, they're quite sound. But you need to use, I wouldn't use a lower class than a 12.9 here, which can handle about 100,000 pounds of tensile strength. And you need rigid bolts for these mounts. Now the reason why I ran 2 or 3 stringer beads over my root passes was because I was using 1/8 inch rods. This is 1/4 inch plate. Naturally, or by default, you'd probably want to use a 5/32 rod, which would allow you just to make 1 pass on your plate. But I was using 1/8 inch rods, so I therefore made sure that the leg was a little bit more than the thickness of the metal plate that I was using. What is the leg? If you look down on a weld and then come out from looking down, the look down distance from the edge to the end of your bead is the leg. And that leg needs to be thicker than The width of your total bead needs to be thicker than the plate, at or more than the thickness of your plate. That's why if you're welding 3/8 inch plate or half inch plate or inch plate, you see a welder running a series of stringer beads over a root pass. They're all just layered on top of one another. But the look down width from this edge to the edge of the bead here is called the lag. And that look down width needs to be thicker than the thickness of your plate. So naturally, if you had a 1 inch, this was 1 inch plate, the look down leg width would have to be 1 inch. So you'd have to have a series of stringer beads wide enough to make the look down bead width equal to the leg or the thickness of the plate. Another issue I had to be very careful about when using 7018 rods was that if you start an arc with a greater distance, there's an air gap, a wider air gap between the tip of your rod and the surface steel, you'll get porosity. So you have to go through any starts and stops or anywhere on your bead where you see small holes where gases came out because it was too hot. And then you have to grind those off and then repair those porosity areas. I only had a couple regions where there were some starts. You commonly don't get them on stops, but you get them on starts if your stick comes up too high. There's too much of an air gap between your stick and the steel, the surface steel. So I was quite fortunate. And then it worked out that I only had to grind down a couple spots on some starts and then reflash those over, and then they were repaired. And the reason why you're doing that whenever you see porosity, you'll see some very small holes. A half of a millimeter, they're very small, but you'll see it'll look a little bit like a spongy surface. You have to grind those off and then weld that and repair it. And you don't want to leave those holes because they can form cracks and they compromise the strength and durability of your welds. So they're compromising to the structural strength of the welds that you're laying down, and therefore you have to hunt them out. Now there are about 15 reasons why porosity can occur when you're welding, but at least for 7018, porosity is it's a well-known rule of thumb when you're using 7018 rods, because if you start your arc with an appreciable air gap between the steel and the tip of the rod, you'll see porosity. And I only had that a little bit. Now, if I were to use 6011 rods, it's very forgiving, and you're not really even going to see a lot of porosity or anything. But 7018, you get the added benefit that it's a stronger 70,000 pounds tensile strength. So with anything that's beneficial, you need to pay a little bit. You get what you pay for. So you got to work a little bit harder with 7018. But at the end of the day, it'll provide a more sound and more reliable and stronger weld than 6011 or 6013. Although 6011 is very, very forgiving and commonly doesn't end up with porosity, and it's almost a little bit more self-leveling. 7018 is less forgiving. So 6011 is typically, you'll end up with a lot smoother beads with little porosity if you do have an air gap at your starts. But overall, if you work a little bit harder and pay attention to what you're doing, you'll end up with fairly decent beads for 7018. I was a arc welder in the auto industry when I was at home in the summertime during college. So I had about 4 years of arc welding experience in a major industrial environmental setting. That is the auto industry. So I got quite a bit of experience on at least welding. So it's all like riding a bike. I do MIG weld a lot now, but I didn't want to MIG weld these because it's a structural system. It's structural steel, plate steel. A lot of people do use MIG on plate, but I went with the rule of thumb that you should use arc welding and 7018 rods for plate steel, low carbon steel. So there you have it.